Okay, so today we're going to talk about actual limit laws and talk about how we can find limits without necessarily using a T-chart, which would probably be nice. I will say, no matter what, when I am given a limit, even now to this day, if it's something that I just don't remember the algebraic trick to, I always go back to a T-chart. So if it's a limit to infinity, if it's something I look at and I'm like, I don't remember that, I always kind of fall back to a T-chart. So that's why we've been focusing on T-charts so much. But today we're going to look at a few other little things. So, question: what functions are continuous on their domain? And what we're thinking of when we say continuous on their domain is if we plug an x equals some number into f of x. Oh, holy cow, my brain. And get a number. Then we say x is continuous, or f of x, at x equals a. So if we think of functions that are continuous in their domain, it's like we know that the function's domain is this. Is it continuous everywhere on that? All of the functions that you guys have seen so far in pre-calc and college algebra and everything like that have been continuous on their domain. It's really hard to make a function that is not continuous on their domain. Really difficult. So we have polynomials. So something like y equals x squared, y equals x cubed. We have rational functions. So y equals 1 over x, y equals x over x minus 3. All of these are continuous on their domain. So I'm just going to start listing off a bunch of these. We have exponential functions. So exponential, logarithms, trig, square roots, absolute values, are all continuous on their domain. And the fun ones to kind of think about this is the rational functions and the square roots. Rational functions, we know, have asymptotes typically. But where their asymptote occurs, we don't include that in their domain. So a rational function is continuous on its domain. That's kind of the biggest part there. It has to be on its domain, and when it has an asymptote or it has, like our square root function only looks at the real numbers when we take the square root of it. So normally square root functions look something like that. They might not exist somewhere, but on their exact domain, they do exist, and they are continuous. There's no jumps, no holes. So any questions about that? It's kind of hard a lot of people have trouble getting their head wraps around the fact that these functions aren't continuous everywhere, but the fact on their domain. So that's like, it's kind of the key phrase that you'll see on your test is on its domain, is this thing continuous? And I know when I ask that question, a lot of people will graph it like, oh no, there's a square root, or there's a hole, or an asymptote, or a hole, or it does something weird, so it's not continuous. It's like, hold on its domain, it's continuous. So that's kind of the key phrase there. Hint, hint, wink, wink, something like this will be on your test tomorrow. All right. So the second question says, if we combine a continuous function together, are they still continuous? And the answer is kind of. So I'm going to answer this in two parts. Yes, if we combine them using addition, subtraction, multiplication, division, or composition. A little circles composition. So if I take sine times cosine, or sine times tangent, even though tangent has all those vertical asymptotes in it, the new domain that function exists on, this brand new function is continuous on that little bit of a domain. So when can this probably seems kind of pointless at this point. It's like, okay, everything's continuous on its domain. How can I combine functions so that they are not continuous on their domain? And so if we combine continuous functions together, are they still continuous? And it's a no. I'm going to put in parentheses sometimes. If we use piecewise. So remember, a piecewise function takes a bunch of functions and we look at it from x less than some number, it's this function, x greater than another number, it's this function. And that's how we get those discontinuities on their domain. So if we use a piecewise function, I do want to point out that if a piecewise function, so piecewise functions typically look like something like that. You have that jump there. However, if I was to take a piecewise function and it closes here and then starts here and goes, it's still continuous on its domain. So you just kind of have to watch out for that. That's why I put it in parentheses as sometimes it's not true. More likely than not, if you see a piecewise function and you're looking at one of those points, it's not continuous on its domain. Does that make sense? No, it's a weird distinction that I'm trying to pull across. So what's so useful about a function that is continuous? Why am I going on and on and on about this function being continuous? And it goes back to our limits. If a function f of x is continuous at x equals a, then what's true is that the limit as x approaches a of f of x, that is equal to f of a. Okay, so I just wrote a bunch of math garbly goop fun stuff. What does that mean? So remember how if we're looking at a limit and I'm looking like as x goes to 3, I'm going to make a t-table coming in from the right of 3, coming in from the left of 3, and I'm going to see if they pair up to find that limit, right? Well, if you know that function's continuous on its domain, and that function's continuous at that x equals a, then all you have to do is plug a into the function. You don't even have to make a t-chart anymore. You just get to plug that number in and find that y value. So it makes life a lot easier. So typically a t-chart just plug x in. So any questions about these? You guys are super, super quiet. All right, so we have this example 1. Is the following function continuous on its domain? Explain. So I want you guys, since you guys are sitting so far apart, just think about this for a second. Is x squared minus sine of x continuous on its domain, and why might it be continuous or not continuous? Okay, do you guys have a kind of idea?
Would it be continuous since they're combined by subtraction?
I'm gonna write that down. Continuous since I'm going to leave a blank there. Combine by subtraction. What is being combined by subtraction?
Polynomial or trig function.
Yeah, so continuous since a polynomial and a trig function are combined by subtraction. Let's go a little bit further in depth. Let's pretend we're talking to someone who really doesn't know this. So it's continuous since we have a polynomial and trig function combined by subtraction. Is the polynomial function continuous on its own? Yeah, so, and polynomials are continuous. And are trig functions continuous by themselves? Yeah. So polynomials are continuous, and so are trig functions. So something to say that on their own, they're continuous on their domain, and how we combine them together, they were continuous on their domain. Does that make sense? Another way to kind of organize this, I am perfectly fine with this, but another way that might be a little bit more bullet pointy would be x squared is continuous. Sin of x is continuous. They are held together by subtraction, and therefore x squared minus sin of x is continuous. So those are kind of the four things that I'm looking for, which we got up here. I know on tests and things like that, people panic and they put either way, way, way too much, or they'll just put like a brief sentence. But on your test tomorrow, when you have a problem almost identical to this, you're going to want to kind of have, oh, that was squeaky, have those four things. So any questions about this? All right, example number 2. Evaluate the following limit. If the limit does not exist, explain why. So we said if our limit is continuous, we can just plug in our number. On its domain, is a logarithm continuous? Yes. On its domain, is a polynomial continuous? We're holding them together by composition. So is this function continuous? So what we are allowed to do is by continuity, we are allowed to just plug that number in. So I'm going to go off to the side. Since log base 2 of x minus 2 is continuous, on its domain, maybe I want to take out that sentence. So log base 2 of x minus 2 is continuous on its domain. Since log is continuous, x minus 2 is continuous. Because it's just a polynomial. And they're being held together by composition. The only thing with limits is they need to be continuous at that point that we're going towards. So here we're going to x equals 10. So we're assuming 10 is on that domain. If we plugged it in and got did not exist, got infinity or something weird like that, then it's not on its domain. So when we can't use this continuity trick. So what we know, since it is continuous, is that this is equal to just f evaluated at 10. And f evaluated at 10 is equal to log base 2 of 10 minus 2. And so we get log base 2 of 8, which is equal to 3. And on your test, unless I'm asking, so on your test, you'll probably have one like each of these. One of these, is it continuous on its domain? I'd kind of expect for you to kind of go through all of those pieces. If I'm just asking you to evaluate a limit, you can use a t-chart, unless I say don't use a t-chart. But if I say you can use a t-chart, use a t-chart. If you can just plug it in, feel free to just plug it in. But when you plug it in right here, put by continuity. And I didn't leave myself enough room. So just beside where you plugged it in, just say by continuity. So you're telling me that the function is continuous there.
Can we get a calculator on the exam or not?
Oh yeah, you can use the TI-36s or the TI-84s, or as long as it's not a like TI-89 CAS or something like that. Yeah. I guess I should have said that at the beginning of the semester. Bring a calculator. Okay, any questions about this? No? Okay. Yeah, it's pretty much just plugging in the number, but just as a reminder, when you do, say by continuity, or write out this whole little paragraph over here. All right. So let's look at the next example. And again, I'm going to work this with you guys. If we just plug 5 in, what we get, so if I said that this equals f of 5, when you plug this in, what you get is 0 over 0, so it does not exist. But we made a big, I guess I forgot a step. 5 squared minus 6 times 5 plus 5 over 5 minus 5. What did we assume when I plugged that 5 in? What assumption did we make before? How about this? Why was I allowed to plug the 2 or the 10 into the top problem? It was continuous on that domain. Is x squared minus 6x plus 5 over x minus 5 continuous at 5? No. So this method doesn't work because technically I should have said by continuity, but it's not continuous. So this whole thing that makes me sad. So that doesn't work. So not continuous at x equals 5. So something we can do is make a t-chart if we really, really wanted to, or there are some algebra tricks that allow us to still use continuity and rewrite this function so that it looks more continuous at its domain. And we call those kind of removable discontinuities. So we're going to remove where it's discontinuous at and be able to find the limit. So the trick, we have the limit as x goes to 5 of x squared minus 6x plus 5 over x minus 5. This is how you would do it if I told you can't do a t-chart. Looking at that top, what could we possibly do to it? If you're in an algebra class and I gave you something like x squared minus 6x plus 5, what would be your first instinct? Yeah. Normally people just have this strange urge in math to factor everything. In this case, that's the right approach. So we're going to redo this. We're going to write this as a limit as x goes to 5 of x minus 5, x minus 1 over x minus 5. Now, what do you notice on the top and bottom? They're going to cancel. And because they are a limit, we can still cancel those out and plug 5 back in. So we get the limit as x approaches 5 of x minus 1. When we cancel things out of a rational function, we typically say, like in this case, we would typically say, oh, but x can't be 5. We took it out, now we can't plug it back in. But the nice thing is, at a limit, we don't care what's happening at that point. We're not actually looking at that point. We're just looking near it. So now we can plug 5 back in. And we get that this is 5 minus 1, which is equal to 4. So this allows us kind of to cheat that continuity system. And I'm going to put by continuity on my 5 minus 1.
So then 4 would just be an acceptable answer then?
4 is the answer. If you had made a t-chart, you would see that's going to 4. However, on the test, this would be the type of problem that I would say, don't use a t-chart. Try and do the algebra for it. All right. Any other questions about this one? All right. We are actually going to skip number 4. There is when you plug 25 in, you get 0 over 0. And there's a trick that you can use to solve this. But later in the semester, I'm going to teach you a way, way easier trick. It's called L'Hopital's rule of dealing with this. And so we're just going to skip this one for right now. The algebra gets really messy. It gets a little bit tricky. I will not test you over something like this example 4. which kind of gives you a dead giveaway that you're going to see something like this. Okay. So